R means resistance and C means capacity.
Correct. Oh, where's my picture? Come on.
We should change it to you.
Change the TV. TV's great.
I think something's wrong with it.
This could be Connell. What's Connell? Oh, exciting. Hello?
Are you?
Hey, I am, but my students are anxiously looking at me now with wonder, just to double check what the plan is for the exam. No, they don't, but I just saw it and I was just wondering about it. What day? Yes. We could, so does that mean they have a week of classes and exams? Okay. So, if it is going to be the later the better, so if I can't take Thursday, then I will definitely want to take... Is that... Okay, that's grand. So, are they? Do they have anything before that? I can still have my classes with them earlier in the week. Yeah. 2 on Tuesday. Yeah. Okay, so I'll have 5 before the test then. That's grand. Okay, thanks for that, so. Great news, the test is next week. But the latest I can make the test is Thursday afternoon. That's the plan, so that's the latest. And I'll still be able to do 5 classes Monday, Tuesday, Wednesday.
Is those 5 classes, the materials in those 5 classes going to be an exam?
Yeah, but I think today we're doing RC, and we have 2 classes, so I'll do RC. Now Kirchhoff is a double, but you can do it in 1 class. I don't necessarily need 2. How many more classes do we have this week? 2 more tomorrow.
Yeah. But one is just...
Oh yeah, but we'll change that into physics class. Because I can always make the assessment due after the break. There's no problem with that. So if I have 5 classes next week, I can do this last one on the first class, and that gives us 4 classes for revision. Now what I would like to do for the revision is that book I gave you, the exam prep book. I'll do questions from that book, because the way I have the exam for you is section A is like about 12 short questions, and section B you have to do, I think, 2 big questions, but my big questions are actually just 3 or 4 short questions. Yeah, so effectively the exam is just lots of short questions, like what is in the exam prep book or what you have for the homework. So since we've done the homework ones, if you want to practice something new, you can try the exam prep book, and then for those 4 days next week we'll just do whatever questions you would like me to do from the book.
Which one is the first then?
Huh?
Which one is the first we should then? Book or...
Oh, which is more important?
Yeah, homework or...
They're equally important.
Not really.
But I would think it's better for you to try questions that you haven't seen before, because then this truly tests if you know the material. So if you can do these exam prep questions which you've never seen before, then that's good, because it means you understand it. But if you can do a question that you have seen before, then maybe you are just remembering how you did it last time and not understanding it. Do you know? Yeah?
Do you get for your knowledge?
Yep, you do. I think it's on Moodle if you want to see what you get for the exam. Anything else?
Have you uploaded the answer yet?
You didn't email me to remind
I
me.
did. I sent you a comment.
You did?
I did.
Oh, I'm so excited. I didn't check my YouTube comments yet, so
I sent it yesterday.
did you really?
I did.
That's exciting. What did you say in the comment?
I said, hi, this is a reminder to upload the answer and a kernel of our exam.
Wow. I'll get to see this later now for lunch. Exciting. Okay, I'll do that. I'll do that after lunch today then. Okay, back to this now. This just turned off now. Right. So as I was saying, RC circuits and graphs. Not too difficult this first lesson. Come on.
I think something in this lesson, because it shows something like standby.
Oh, did it? Oh, okay. Let's see. Try and get it back. There we go. Okay. RC circuits and graphs. Did you write that down? Yep. So, not too much to do in this lesson. It's not so bad. So let's have a look at the capacitor a capacitor is fully charged up like in a camera, and it then is suddenly allowed to discharge, release its charge, through a resistor. Let me draw the diagram. So what you have is something like this. Come on, keyboard, what the heck? Okay, and we're back. Okay. So here's my capacitor, and let's say here is my resistor, which could be like a light bulb, and we'll say the current flows this way. So this is a very, very simple circuit. Now, in real life, it might look more like this. I'll just show you here. You've got a little switch here. So what happens in real life is you put the switch up here, and then the current flows this way and charges up the capacitor. And then what you do is you flick the switch down, and then there's no more battery or no more cell. So then the current flows out of the capacitor then. So it's a bit like when you press the button on your camera, what you're doing is you're like flicking this switch here between charging and discharging. Yeah. So this is a very, very, very simple circuit for how you can charge up a capacitor and then discharge it. So first thing I'd like you to do is to draw this. Now, in the exam, they don't actually care about the charging up part. So for the exam, it's really this part that you're interested in. But if you want to know how it managed to charge itself up, it's because of this connection on the top. Oh, this is the part that we care about.
No, the rectangle box is that one.
This one?
That one.
This one?
Yeah.
The resistor, which could be the bulb of the camera, or in the defibrillator, it could be the person's heart. Many things. Okay, got that? Yep. Now, oops. Notice how this circuit has one resistor and one capacitor. So we call this circuit an RC circuit, which is the name of the lesson. Let me add in an ammeter to measure the current. So what I'll do, I'll just stick here, for example, we'll just stick an ammeter there, so I can measure the current. And here's a table of maybe the measurements I got. So here is the time, and here's the current in milliamps. So it takes 10 seconds here for this to nearly discharge. And you can see we're decreasing the current here. So what I would like you to do is just to copy this table down as an example of data you could get from such a circuit. Open up. So this is current in milliamps against time in seconds.
Why the current is decreasing?
Oh, because the capacitor is discharging. Discharging through the resistor. Got that table, Darius? Yeah.
So then, like after the switches turn off, then the current will flow another way.
Yeah, you flick the switch, disconnecting the cell, and the capacitor starts to discharge. So while the switch is up and it's charging up, the ammeter is 0 because the circuit is broken down the bottom. Then when you flick the switch down, the current flows in the bottom circuit and the ammeter shows a current. But this actually starts decreasing straight away as the capacitor loses charge. Yeah? Continue? Continue? Yep. So, what do I want to do next? As you can see, the graph is decreasing exponentially. So let me just draw that for you. So my first column will be time in seconds, and my second one is current in milliamps, and my time starts at 0 and increases to 10, is it? Do I go up to 10?
Yeah.
My current starts at 100, isn't it? And then it's 70 point whatever it is. I'll do 2 decimal places. It decreases down to 3. Let me graph this for you. Insert chart, and we'll make it a scatter, and we'll connect the points for fun, and we'll call it current against time in seconds, current in milliamps. And you can see it has this nice smooth exponential decrease to it. Let me just move that a bit out of the way so we can still see the data. Okay, is that okay? Yeah. So just very roughly draw this beside your table. Just a rough, quick sketch. Got that? Yeah. So as you can see, this is exponentially decreasing, which is maybe not a surprise. So we can imagine the equation being something like this with an E in it. You've done these graphs in maths class, right?
Yeah.
Yeah. So what we're going to do is we're going to imagine for this graph that the current is some constant e to the power of the time divided by some other constant, and we don't actually know what these constants are yet. It's difficult to get these constants from a curved graph. You could probably figure out the I0 from this graph. What would you say the I0 might be? 100. But what is not easy to do is this constant in the power. So we need some trick here to get in the constant. We can see the I0 is the initial value, but what the heck is that constant? It's a bit like the K. So the trick here is to use logs. Now, before I continue, I will say what I'm about to do is a proof in the exam. In the exam, they sometimes ask students to start from here and prove the formula I'm about to show you. So please write this proof down carefully. I think this might be our first exam proof. Is it? Did we do anything before this? No, I don't think so. Because the other one is in semester 2. Huh? The UVATS?
Yeah. Negative T power E power negative T over.
Oh yeah, what the heck is that? Anybody know this letter? It's a Greek letter. Go? No. Go? No. Goko? No. Gugu? No. Tau. Very good, yeah. Tau. It's a Greek letter. Tau. Okay. It's a Greek letter. I will explain what it is now after the proof.
Okay.
So, what we do is we put log on both sides. Now, on the right, you can change this into log I0 plus log E minus T over tau. Yeah?
Yes.
Because that's the first rule of logs. And then what can we do with the power here?
Without.
Yeah. What's log of E? Does anyone know?
1.
1. So I can write this as log I equals minus 1 over tau T plus log I0. Now if I say call log I, just call that Y, and log I0, T, X, then you can rewrite this formula as Y equals minus 1 over tau X plus C. So my point is, if you make a graph where you put T here and log I here, it should be a straight line. Oh, sorry, I wrote C. I meant to write here log I0.
What is the graph? The slope is.
Oh yeah, I haven't talked about that yet. Now, if this is compared to y equals mx plus c, we can notice that the slope must be minus 1 over tau. So on this graph, the slope equals I think I'll say it the other way actually. The tau is equal to minus 1 over the slope, the m. And the c here, you can use that to get log I0. But you don't really need to do that because you know what the I0 is. It's this part that we care about here. Let me show you that on the graph. But this proof, the proof that the m is minus 1 over tau, is on the exam. Any questions with this? I don't know because I made your exam so long ago.
Where did you get the time from? No.
Sugar? Continue?
How did you get the equation that tau equals?
How do I get to what now?
When tau equals to negative 1.
Oh yeah, because m equals minus 1 over tau. I'm making a comparison. Yeah? Yeah?
But then tau is negative.
No.
But the shape is.
Oh, I drew it stupid.
Yeah.
The line is going down,
Yeah.
not going up. Yeah. When you graph this, your line should be going down. Continue? Okay. Are we just waiting for Bruce?
Okay. Nothing.
Not waiting for you? Okay, continuing. Continuing. Yes.
Yes.
Right. So let me graph this. What I'm going to do now is, instead of current, I'm going to have a look at log current. Now just let me calculate that first. Equals log, oh flip, equals log. Okay, how many do I need? I need a few, don't I? Right. Paste only numbers. Well, hey. So this has now become, come on. I want to change this to, there you go. Log current, log milliamps. Wonderful. So if I calculate the log of the current and graph that, do you notice how I get a perfectly straight line? And we can use the slope of this line to get the tau. Let's calculate the slope of this. Slope is the y over the x.
Yeah.
So here, what's the y? Let me see. It goes from 4.5 to about 1. About. So that's about 3, isn't it? And what's the x? About 3. Okay, about 3. Forgive me. So that's about 3. And what's the x?
10.
The x is 10. So 3 over 10?
3 point something.
0.3.
Yeah.
About. So on my graph, I can see that the m is about 0.3. Well, minus 0.3 because it's going down. So the tau is roughly 1 over 0.3, which is about 3. Roughly. Now we actually haven't said what's the units, which we'll have to get to in a second. Yeah, the units of the tau. That's the units. Can I continue? So, here's my table. I've just recalculated. This is very common in the exam. A trick in the exam on students is they ask you to make a suitable graph for current and time. One mistake students make is they forget that it's more suitable to calculate the log of the I before they make the graph. So once or twice I would see a student plot I and T. Instead they should really plot log I and T. So you would need to calculate this yourself in the exam. Yeah, it's no big deal. Just use ln on the calculator.
Let's use the
It's not that long. Come on. No, it's, yeah?
What's the difference?
Between what?
RC and the log
Ah, well, if you plot the log, you'll get this shaped graph.
That's why.
Huh, why? What do you mean, like why? Why not? Or what are you unhappy about, my log graph?
Why the shape is changing?
Why do we do that?
Ah, because you can only get the slope of a straight line. And we need the slope to get the tau. In physics, we prefer our graphs to be straight lines too. We don't like curvy graphs, unlike biology. For physics, we want a nice straight line graph. So we can make the current a straight line if we get the log of the current. Okay, continue. Yeah. So, we saw that if we have this, and we put log on both sides, we can get this formula. Where this we put on the y-axis and the time we put on the x-axis. Y is log I, x is t, m is minus 1 over tau, and c is log I 0. What I would like you to do is to write this down, please. Got that? Now we still have to ask what are the units for the tau, which we'll do that in a moment. Continue. Yep. So, think about this. If I say I equals I0 e minus t over tau, you have your triangle VIR. So, if I multiply both sides by OR, what does this become? This becomes V, because V is IOR. So you can easily change this formula into this formula. Same thing. So both the current and the voltage decrease exponentially. So not only does the current behave like this, but so does the charge, and so does the voltage. As long as R is constant, which we'll assume it is for this circuit. But we haven't talked about the tau. What is the tau? We actually call the tau the time constant, and we have a formula here for it. What's the units? Let's examine what the units are before we write this down. So I said tau equals minus 1 over m, the slope. So that means the units for tau will be 1 over the units for m. But remember, m is the y over the x on the graph, the height over the base. So that means this will be the units for x over y, because it's upside down, it's 1 over m. Now if I think about my graph, there's my x, there's my y. What's on the x? The time. Yeah, so you would have something like t2 minus t1 over, and then here this will be log I2 minus log I1. You know the formula for maths, y2 minus y1 over x2 minus x1. Now what's the units for t? Seconds. So what's the units for t minus t? Still seconds. Seconds minus seconds leaves you seconds. So that's seconds there. Now what's the units for log I minus? Now you see, this is where you have to be careful, because you can change this into this, right? Now what's the units for I? Amps or milliamps. And for this I? Amps. And what's the units for an amps over an amps? Cancel. No units. So the units for time, tau constant, is seconds. Yeah. So the tau is in seconds. I think it's good for your education to write this down. Good experience, I think. By the way, this is another reason why we like using logs sometimes, because you notice that the tau doesn't care about the units on the y-axis. Even though it's the slope, in fact the units for the tau will just be the units that was on the x-axis. The y-axis disappeared from the units because of the log relationship with the i's. So this is actually an advantage as well. It means we can use amps, milliamps or kiloamps on the y-axis, and this does not affect the value of tau. Interesting. Okay, continue. Got that? There is another formula to get the time constant. Oops. I'm sorry, does everybody have this? Yeah. There is another formula to get the time constant, which is actually, we don't do the proof of this one. If you know the R, the resistor, and you know the C, the capacitor, in fact, believe it or not, if you multiply these, you get the time constant. Continue. Now, yeah. Oh yeah, no, go ahead, Joe.
Which one is the more useful?
Both. You need to use both. Yeah. It depends what you know. If you know the R and the C, then there's no point in making a graph because you can get the time constant. If you don't know the R and the C, then you must make a graph to get the time constant.
Do we need to draw any graph doing anything?
Yes.
Roughly or detail?
What do you think?
Roughly.
Try again.
Detail.
Yes, correct. Alright, continue. Let me just check. If this unit is seconds, then what should this unit be?
Second.
Yeah, well, let's just check. So, OR-C, what's the units for OR? Ohms. And C? Farads. Okay, well, we remember what ohms are. That is joules per coulomb. And farad is charge per volt. So, Q per V, isn't it?
Yeah. Oh, Q3.
Oh, sorry, C. Thank you. Okay, well, what happens here? They cancel, so you're left with joules per volt. Now, what is a volt? A volt is a joule per coulomb.
Yeah.
Is that right? This is very confusing.
Yeah.
Farad is a coulomb per volt, and an ohm is a joule per coulomb. And a volt is a joule. Huh?
R equals V over I.
R equals V over I. Oh, at the beginning. Yeah, that would have been smart. Too late now. No, that's not right, because I end up with coulomb.
I think ohm is wrong.
Oh, something's wrong here, isn't it? An ohm is you lose. Oh, ohm is you lose a volt per. Yeah, you lose voltage per coulomb. Do you know what? I'm going to take her idea, which is we'll get rid of the or from the beginning. So RC, VIR, that's V over I C. That's much better. That. So the units would become volt, and current is coulomb per time, and coulomb is coulomb. No, that's capacitance. That's farads. And that farad is coulomb over volt. This V cancels V, C cancels C, and I'm left with that, which is that then. So yeah, this has the same units as time, seconds. No, don't write that down. That was painful. All right. Okay. Also note the time to fully discharge. So one reason we care about the time constant is also, if we know the time constant, we can know how long until the capacitor discharges fully and loses its charge. It's 5 time constants. Now in real calculations, it's not actually 0, because if you think about the graph, will this graph ever reach the x-axis? No. But we say in physics that it practically reaches the x-axis after 5 time constants. So if the time constant is 2, then it will take 10 seconds to roughly reach the x-axis. So the time to fully discharge is 5 time constants. Bruce and company. Calvin, did you write this down?
Yes.
No surprise that the units are seconds. I don't know why I said no surprise the units are seconds, because we had to actually work hard to show that the units are seconds. I think it's because if I said the time to discharge is 5 time constants, then it won't be a surprise that the unit is seconds. Continue? Yeah. So, we just have the one question, which we'll do together. We have a current discharging, and I tell you the charge and the time, but this is in milliamps and milliseconds, and it's a 200 millifarad capacitor. And the first thing is to graph this. So let me just write the numbers down for you. We start off with 1,000 here, and then the next value is 841. No, that ain't it. Yeah. And then that is the previous number. And then I just copied these numbers into my table here. But of course I shouldn't graph these. What should I graph? The log of them. So let me just again get the log of all these numbers. Whoa! We don't want a problem like last time. Okay, dokie. And we'll just put them there. Paste numbers. Right, now, I have to change a couple of things though, because this is milliamps and milliseconds. So let me just put here milliseconds, and here should be milliseconds. Alright, so I've made the graph. That's part one. Part B, what is the tau? So I would like all of you to copy this graph, and then once you've done that, use the graph and tell me the time constant. I might need to have my calculator open now, so let me just do that too. Log current.
For log I is log milliamp.
The unit for what?
Log current.
It's log milliamps. I don't really think it is exactly that. I'd have to double check. I think I'll double check the way they like it in the exam, but I think they might actually, it's okay if you write log milliamps, but I think they prefer the student to write it like this: log of I, which is in milliamps. I think this is the preferred way. I don't really see a big problem with log milliamps, but if you want to match it up more with what they do in the exam, they write it like this, which you can say is log of I, which is in milliamps, that the I is in milliamps. Yeah, so if you prefer, you can write it like that. Log of I, which is in milliamps. Okay, have you calculated my time constant yet? Of course, you don't need to write these down, or you certainly don't have to write all of the decimals down. Oh, I don't know what I'm doing. Maybe I can just shrink it. Yeah. There we go. Got that? Sure. What do you need to get from the question? What? Well, good thing that doesn't make me too sad. Oh no, that does make me sad. Let's pretend these were milliseconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's my question, I can change it. Yeah. Guys, I wrote down the wrong times here, so if you're copying the times, we're going to make these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliseconds. Oh, okay. Got that? What did we get for the tau? The tau's always positive, so yeah. This calculator will help us here. So what's the slope? Let me see. The slope will be, it's about 7 minus about 5.1, I'll say, on the graph, over 10 minus 0. Oh, and it should be minus because it's going down. So if I just do 1 over this, if I just flip it using this button, and minus. So you should have something roughly like this, 5.3, we'll say, roughly. Yeah, 5.3 milliseconds. Okay, next part. How long until the capacitor fully discharges? So how do I get that? 5 times this number, yeah. So times 5, and that's about 26.3 seconds. Milliseconds. It will take 26.3 milliseconds. How long to discharge? To fully discharge. And finally, what's wrong? Did I make a mistake?
How to calculate the gradient?
They expect you to do it visually in the exam. What I mean is they expect you to take a point and to take a point and do y2 minus y1 over x2 minus x1.
But is it using the log number or is it using the
originals?
Yeah.
No, the logs. Yeah, of this graph, and this graph uses logs. What's wrong with you?
Huh? Can't calculate it.
Well, if you don't believe me, no. If you don't believe me, what we can do is ask Excel to calculate it. Oh, you do believe me? I'll get Excel to calculate it. Yeah, of course, everything's possible. So Excel says the gradient is minus 0.17. Alright. Lastly, what is the OR? How can I get the OR?
Tau equals RC.
Tau equals RC, so OR equals tau over C.
Yeah.
Now please be careful.
C over tau.
No. No. Tau equals RC. So that means
What?
tau equals RC. So that means R equals tau over c. Now that is when you're using seconds and coulombs. But what's our tau? It's in milliseconds.
Yeah.
So we should write it in seconds. 0.0, what was my tau?
5.
5.
5, that's 5.
So like this.
Yeah.
And the capacitor, I try to trick you, I give it to you in millifarads. So in farads, it's 0.200. So 0.0053 divided by 0.200. And the resistor is 0.0265, or in other words, 26.5 milliohms. Yeah, is okay? Okie dokie? Yeah. Yeah, that's one in your book. So, just for 5 minutes to try a question from the book, and then I want to start the next lesson. Can I close this slide? Yeah.